Welcome to Study Loop.
Here we consider a cylinder in a z direction with a radius a. So let me write the radius with the red here. That is a. This is in the z direction. Here is the x-axis. So we can represent the z direction by a unit vector k cap. And here is our y. The current density is not constant across the cross-section of the wire. So let's say the cylinder is a wire. So the current is not uniform, it's not constant. We represent this current by, so for part A, J current density is B over R times exponential R minus A divided by delta in the K direction, so K cap. R is the distance from the center, so for a dI current, for element dr here, so dr, whose area will be dA, which will be equal to 2 pi r times dr. Then we can write di will be equal to j times dA using the definition of a current density. Then we can write di, so di will be then j times 2 pi r dr. Then we bring down the j that we wrote here, so we'll substitute this j and find di. So di will be then b over r times exponential r minus a over delta in a k cap direction, so j times 2 pi r times dr. Then the total current passing through the wire equals to the integration over the whole wire from r0 to r is equal to a. So I naught is equal to integral from 0 to a di, that is 2 pi b integral of 0 to a e exponential r minus a over delta dr. Then the integral evaluates into 2 pi b delta e r minus a over a delta from 0 to a. This gives us 2 pi b delta 1 minus e exponential minus a over delta. Then our I naught will be 2 pi b delta 1 minus e minus a over delta. The radius of the cylinder is 5 centimeter, which is a is equal to 5 centimeter. B is a constant, equals to 600 amps per meter. D is a constant, which is equal to 2.54 centimeter. We substitute those values and find I naught to be 2 pi times 600 times 0.025 times 1 minus e exponential 0.050 over 0.025. This gives us the current of I naught of 81.5 ampere. Part B of the problem. Now for R, which is greater or equal to A, the enclosed current is I naught. Therefore, from the Ampere's law, we can write closed integral of B dot dl is equal to B times 2 pi r is equal to mu naught times I naught. From here, B will be equal to mu naught I naught over 2 pi r. Part C of the problem. Now we need to find the current enclosed for R, which is less than or equal to A. We again use the ring with a small width of a dr and area of a dA. Then we can write di will be equal to j times dA. So we substitute the for dA and j. Then our di from r dash is equal to 0 to r dash is equal to r will be di is equal to 2 pi b integral from 0 to r e r minus a over delta integration with respect to dr. This gives us 2 pi b delta e r dash minus a divided by delta from 0 to r. And this gives us I to be, so our I will be 2 pi b delta, b times delta, b times delta exponential minus a over delta, er over delta minus 1. But we know I naught is equal to 2 pi b delta 1 minus e minus a over delta. Then we can write I will be equal to I naught times exponential r over delta minus 1 divided by exponential a over delta minus 1. Part D of the problem. Now we need to use the results from a part C to find the magnetic field for r is equal to or less than a using Ampere's law. Closed integral of b dot dl is equal to 2 pi r times b, which is a function of r. This is equal to mu naught times current enclosed, which we found is I naught. So mu naught times, so we'll substitute this I naught times e r over delta minus 1 divided by e a over delta minus 1. Part E of the problem. Finally, we need to evaluate the magnitude of magnetic field at r is equal to delta, r is equal to a, and r is equal to 2a. For b, r is equal to delta, from the above equation, we can write mu naught I naught. So this is exponential minus 1 divided by 2 pi delta exponential a over delta minus 1. So we substitute the values. So this will be 4 pi times 10 to the power minus 7 times 81.5 amperes is I naught times exponential minus 1 divided by 2 pi times the delta we have is 0.025 meter times e to the exponential, which is 0.050 over 0.025 minus 1. This gives us a b at r over delta to be 1.75 times 10 to the power minus 4 Tesla. For r is equal to a, the magnetic field, similarly, we can substitute those values. R is equal to a, we get the magnetic field to be 3.26 times 10 to the power minus 4 Tesla. Similarly, for r is equal to 2a, we'll substitute a 2a for the given formula. Then we get magnetic field mu naught I naught over 2 pi a, and substituting the value for I naught, mu naught, 2 pi, and a, we get here 1.63 times 10 to the power minus 4 Tesla.